all that, because what we do is kind of very much related now. All right. So what we have seen in linear regression is basically, as I was telling you, response variable was quantitative. Basically, it was a continuous value like temperature or sales value in dollars or rupees, like that. So it is a continuous variable where we were trying to regress the value of it um, using the data, of course, and the independent variables act in a specific way to result in the response. But these are, yes, there are a lot of such physical processes in real world that result in quantitative response. But at the same time, there are a whole set of different problems which are very much interesting to us and more practical, a little more. I would not say drastically more, but a little more, where the response is qualitative. Qualitative means it's not a continuous variable. Instead, it takes specific values from a set of well-defined objects. For example, so the eye color can assume one of the three colors, which is blue, brown, or green, right? It cannot take any other values apart from these three. That means there is a predefined set from which the response variable can assume values from. Similarly, there are a lot of such problems. For example, if you receive an email, it can be either spam or it can be not spam. Generally, it is referred to as ham informally. So what it means is there are only specific set of values such the response variable can take. So these are typically known as classification problems, right? So these values are the responses are referred to as categorical responses, right? If you take a lot of classification problems, for example, speech recognition, when you say a word to systems like Alexa or Siri or even OK Google also, right? You sometimes say some things. So you utter a word and it has to classify, it has to assign one of these words from the dictionary, English dictionary, to what you have spoken, right? It cannot be anything, right? It can be only one of those particular set of predefined list. So these are all classification problems. I'm pretty sure you are all very aware of. But let's try to connect what we have seen in the previous session, which is linear regression, and now what we're going to do, which is logistic regression. Right. So because we know them as classification problems, and there are a lot of ways we go about solving this. Solving this means learning a classifier which accepts the input and gives away the prediction, which is one of the values from the predefined list. So this whole set is called a classification problem. And there are a lot of classifiers, right, from logistic regression, which we are going to see today. And a little more generalized version of it is called linear discriminant analysis. And KNN, K-nearest neighbor classifier, is also very familiar to us, where you don't do any, we do predictions, but we do take voting, basically, right? You look at the K nearest samples to the given sample in the training data and see to what classes all those nearest neighbors are assigned, and take the maximum of that label and assign, right? So if a majority of them are assigned to a particular label, you also assign the same label to the test sample, things like that. Generalized relative models and random forest boosting, all these are different classifiers generally we discussed in machine learning courses, statistical learning courses. SVM is our favorite before the ANNs are revolutionized. So ANNs, artificial neural networks, also is a classification tool which accepts input and predicts the class or label. So yeah, a whole lot of classifiers are there, but most of them draw inspiration from logistic regression, right? So intuitions here work a long way. Similar to linear regression, logistic regression is also a very fundamental classification algorithm, classifier. Knowing it thoroughly is very important, because, as I said, some of these are generalized versions of logistic regression, and it gives you very much interpretability also. What I meant by it is basically assume a spectrum of classifiers from very limited capacity to very high capacity, right? So as you go towards high capacity, what happens is you get a lot of accuracy. Even the complicated problems you can solve easily. Maybe not easily. You need computations and data, etc., etc. But you get a very good accuracy compared to the left-hand side, which is simpler, very limited capacity classifiers. But the problem with these high-capacity classifiers or more sophisticated classifiers is they are not interpretable. You don't understand much of the details. For example, if a convolutional neural network says there is a dog present in the input image, you will not be able to understand why. Maybe it is correct, but as a human, if you want robots to do some of the decisions, algorithms, if you allow algorithms to take decisions, so you want to understand why this particular algorithm classified what it classified, right? So that is called interpretability. So that is very, very important. So because without that, we cannot allow a lot of our day-to-day activities to be taken over by these intelligent systems. Of course, we knowingly or unknowingly, we are allowing the machines to take our decisions. For example, if you see a lot of applications out there for real, particularly in US, these the prisoners who are in the prisons for some wrongdoing, they'll apply for parole or early release, saying that providing all the data and all the stuff. They make an application. The judge uses a AI software where all these features, the input application features, will be fed into the algorithm, and the algorithm will say with what probability he will commit another crime if you release. If it is very small, the judge may release him on parole or early release, right? But he has to understand why the algorithm says with less probability or with more probability this fellow can commit mistakes or crimes. So that is very important. Although we are using, for example, you do a lot of such applications in medical imaging also, in healthcare also, right? Algorithmic diagnosis is very much prominent. You take fMRI or MRI or right from X-rays or retinal images, you train DNNs or AI systems on them, and you ask them for prediction, they will give. But ultimately, as an expert, you have to understand why the system is saying whether there is a tumor in this body, whether there is no tumor in this body. It has to be able to say, right, like an expert, real expert. So that is called interpretability. But unfortunately, these sophisticated models do suffer from lack of interpretability. We get accuracy, but they are not interpretable. But on the other hand, if you look at the other extreme of the spectrum, where simple models like linear regression, logistic regression, things like that are there, they are very much interpretable, right? There were a lot of questions we were investigating, right? We were trying to understand as a developer, as a user. So all this is possible here towards this left extreme, where the models are simple but highly interpretable. So linear model is very simple. Even logistic regression is also very simple, which makes it very easy to understand and interpret. You clearly know what is happening and why it is happening and all that. What you have to do, in order to realize a specific output, things like that. So that is why even now, with a lot of new algorithms coming up in 21st century, so the logistic regression is still being used in industry, because not just logistic regression, both linear and logistic are being used because of their interpretability, right? So that is one important point. So which is the driving force behind their suitability even now, even today. All right, so that's a little sidekick. Yeah. So in those classification problems, we have to use one of these classifiers. So today we'll start with logistic regression, which is, yeah. So similar to the previous session, where we had an example, if you remember, we had an advertising example where the company spends on advertising in various media like newspaper, TV, radio, so that the sales will be increased, right? So let us have a similar or a different example here, basically to understand things, the intricate things in the algorithm. So here we'll take a credit default application where there is a bank where you go and apply for credit, or it was more like this. So you have a credit card. You are given a credit card, and you're spending it and you're using it every month, and at the end of the month you have to pay back whatever amount you have used, right? But if you end up spending more, or if you don't have enough money to pay, you will default. That means you will delay, you will miss paying the deadline. So that is when that particular customer is called a default, or the process is called defaulting, right? So they have collected a lot of such data from a bank where like exactly 10,000 samples, where whether they have paid in time or whether they defaulted, and they collected what is the annual salary income they are getting, and how much was the credit card balance, how much they have spent in the credit card at the end of this month. So if you see this particular plot on the left side, which is on the x-axis, you will have balance. That means how much was the credit card balance towards the end of the month in dollars, whether it was $1,000, $1,500, or $2,500, and so on. The y-axis, it is the annual income of that customer. How much was his annual pay? 20,000, 40,000, 60,000, or anything in between. So it's a continuous scale. So all the blue circles were non-defaulters. These fellows were able to pay in time, and the pluses in orange represent the data points where these became defaulters. They could not pay in time, right? So this is of course you will not see equal number. There will be a lot of customers who pay in time. So for visibility, for visualizing the this class, blue class, only some of the samples have been displayed. There are a huge number of samples that are in blue class, but in the orange class there are only small number, 1/3, exactly 1/3. Yeah, I think so. It is 1/3. Yeah, I might be wrong, but anyway, it's considered that it is lesser than the blue class. Obviously, as we can understand, a lot of customers do pay to avoid penalties and all that. So if you see, as I said in the last session itself, so visualizing the data is very, very important. It tells you a lot of things, right? It gives you intuitions to design algorithms for solving automatically. Whatever you think is the right way to solve this problem, you can just translate that into the algorithm, right? So that is what is required when we start with a problem, particularly in machine learning and AI. You have to visualize the data. A lot of data science hype is going on now. So some of you might also be part of data science projects and curriculum. So this is the funda. So data needs to be visualized. Data needs to be understood, right? It needs to be studied, not algorithmically. That will come definitely as a second step. First step is humans as developers. This is our first thing to do. We have to visualize. So you can clearly see. So what do we understand from this simple graph? So yeah, the orange plus symbols are more towards the right side. What that means is, typically all these defaulters had higher balances, right? Towards the right, the balance is more, right? That means they spent more, right? This is not a great finding. You can even suspect without even looking at this graph, right? If they are defaulting, if they are not able to pay, maybe they are spending more. That is why they are not able to pay back. So that is one observation, right? And more or less same. So if you see across different income ranges, right? This can be high pay, this can be low pay, this can be medium pay. Seems like it is spread. It is spread across all income ranges, right? So the defaulters are there with high salary, medium salary, and low salary, right? It is not concentrated only in one of these income ranges. So that is also understood from visualizing this data. Anyway, so that can be inferred in another way. So what the second and third plots do tell us is, basically they plotted the balance against the default class, whether they defaulted or not, right? So if you see, this is what I was saying. If you look at the yes for default case, this is where people fail to pay back, they delayed. So this is for this class, y-axis is more, like high value is there. That means balance, the leftover, the credit card spending was more for this class, right? So you can do, projecting onto X and projecting onto Y, you get this kind of plots. We saw that already. This kind of inference we already saw, because we observed that the pluses are more towards the right, so balance is more. That may be the reason why they failed also. And if you see the second graph, it is not much informative. Why? Because for both no class and S class, income ranges are not very different. They are pretty much the same, right? So it's not that only a subcategory of income ranges are behaving in default. No, it is not like that. But anyway, this also we could see, right? It was spent all over, spread all over in the income range. So this is important first step we have to do as part of a data science development. All right, so let's proceed. So what do we predict generally? When we attempt to solve a classification problem, what do we predict? Do we predict the system? Do we want the system to predict the class label directly? So in a way, yes. So what classifiers generally predict is the probability for each class as a quantitative variable, right? So this is what we wanted, right? Probability basically is a continuous value between 0 and 1. So we want a predictor which predicts that value, a quantitative response. So if it is more, let's say if it is 0.9 or so towards one class, you will say yes. For example, the probability for one of these inputs to be default is 0.7. Yes, now it makes sense to think or believe that fellow will default. That means he will not pay his credit card bill, right? So that way, if you look at that aspect where the probability is being computed as a quantitative variable, it makes us to use the regression models. So regression, if you recollect linear regression, we were predicting y is equal to beta 0 plus beta 1 times x. So it's a continuous variable, also known as quantitative variable. So we can still use, even in the classification problem, we can use a linear regression model, any other regression. Basically, quantitative variable can be used because the probability we can model it and predict it, right? That's what I was saying. So why not linear regression itself? Now that we understood linear regression from the previous session, so why can't we use the linear regression model to predict the probability towards one of the classes? Let us say we are interested in default class. That means the category of the people who will not be able to pay the credit card bill in time, right? So that is called default class, right? So why can't we use the linear regression? Let us use that. So suppose, okay, we'll go to this particular example in a minute, but let us try to understand a generic problem where you will have more classes, right? It's understandable. Not every classification problem will have only two categories. There will be more categories. For example, consider a medical diagnosis situation where a patient will be diagnosed. Some blood reports and some other reports will be input in order to classify whether the patient is suffering from stroke or drug overdose or epileptic seizure. These are three different health conditions. Let us say, based on the inputs taken from the patient, the objective is to diagnose or classify his or her illness into one of the three categories. Let us say I want to assign label value 1 to stroke, value 2 to drug overdose, and value 3 for seizure. And now let us investigate whether we can use a linear regression, because if let us say if y is being predicted close to 1, then we can assign label stroke. If it is close to 2, we can assign drug overdose, etc. So this can be posed, but there is a problem. You can all understand why a linear regression cannot do a classification. Why? Because so this particular way of assigning labels is problematic, right? It is kind of ordering the outcomes. In a way, it insists the differences to be same. 2 minus 1, the difference between drug overdose and stroke is same as epileptic seizure minus drug overdose, right? So if we model a linear regression to predict the class labels of 1, 2, 3 for these 3 diseases, what it means is basically the differences are equal, as if we are saying the system that so the degradation or the type of things that deteriorate the health condition from stroke to drug overdose is same as taking the condition from drug overdose to seizure, which is meaningless, right? It may not be true at all. Most likely it is not true, right? So there are 3 different diseases. The distance between each of them numerically, uh, which is same, should not be same health wise, right? In the real world it doesn't correlate that way. So that is the problem. For example, if you assign 3 different labels, brown, uh, blue and green, let us say you are classifying the eye color of a patient or any other person. So you read the iris, the image of the um, eye, and you want to predict based on the quantitative response 1, 2, 3. Does it also has the same problem? Brown minus blue is same as blue minus green. That means the distance between blue eye and black eye, sorry, blue eye, brown eye, and same green eye and brown eye is same. That's what the labels say, which is meaningless. So that is the reason people generally don't use regressors for classifying. We need to have a separate technique for classification, right? So this sometimes people understand, sometimes I see students don't understand it easily. So that's why we have 2 branches in supervised learning itself, because one is towards predicting continuous variable regression, one is towards predicting a categorical variable, which is taking only specific values, not any value in between, right? There will be, as you see, there will be only 2 classes, default or no default, right? So that is why this, in fact, this is more real problem. In real world, you want to see a lot of uh, predictors to take only specific values, right? So that you all by now you all understood, or you are maybe aware that classification is the most solved problem in machine learning, right? So a lot of practical problems will be posed as classification, and we train classifiers to predict the label, right? All these examples, whatever I have said, whatever I was sharing, right? Banks use whether to give the loan, whether not to give the loan, whether to give a credit card or not to give a credit card. And the prisoners in the US, they use this kind of classifiers. The judges, they use this kind of classifiers, whether to give parole or not to give parole, things like that, right? A lot of algorithmic decisions are classification. So it is very well studied, particularly in the last 3-4 decades, maybe a little less also. All right. So that is the reason why we can't use linear regression, because it will separate and the differences it assumes to be same between label 1, label 2, and label 3. So that is not correct. That is not meaningful also most often. So maybe there is one case, maybe if the response variable itself takes a natural ordering. For example, only one disease you are investigating, let us say cancer. And also, it has 3 different stages, mild, moderate, and severe. And also, if we know that the gap between the mild and moderate and severe is similar, right? Only then you can classify, or you can assign labels 1, 2, 3 to them and use a regressor. But this is very unrealistic. But maybe there is a small subset of problems where this holds true. In that case, we can use regressor, linear regressor, any other regressor to model the classification problem, right? So I want to warn you, not every time, but only the ordering itself is natural, means which is more meaningful. It is not we are assigning, right? If we are assigning, we can assign in any other way, right? I can say stroke is 3, drug is 1, and epileptic seizure is 2. So because it is not natural, anybody can come up with any order. That is why it is not meaningful. But this case where a particular disease will have different stages, and the deterioration is more or less same, mild to moderate, moderate to severe, the gap or the intensity required from going from 1 to 2 and 2 to 3 is same, in that case, maybe it is meaningful and you can go for modeling using a linear regression, but not generally, right? This is a very special case. So I want you to remember, this is only a special case. All right. Yeah. So that is about why we are not. There is also another reason. I think we'll come back. So let us consider a binary qualitative response, right? Which is binary classification problem, where there are only two classes. Now we can assign class 0 and class 1, right? This is also possible because there are only two categories. You can model the probability towards one class as a regressor, and if you don't need any other variable, only probability towards, let us say, class 1, you can model using a line or linear model, right? Beta 0 plus beta 1x. As it is higher, the value predicted for the value y is higher. You can assign category 1 to that input. As the value goes towards 0, you can assign the value stroke to the input features, right? So this is also a special case where there are only two labels. In that case, you can predict using a linear regression. You can still use the regression techniques that that are there, right? So as opposed to the previous case where there are more labels, but their ordering is natural, which makes more sense. That case you can use. And if there are only two labels, then it doesn't matter, right? There is no comparison between, the distance between 0 to 1, and there is nothing else to compare. So we can assign 0 to one class and 1 to other class. Even if you change the ordering, it doesn't matter. It is still the same problem. So this is also another special case where you can use regressors to classify between these two classes. But there is one problem. As we said, the probability always has to be within 0 and 1, right? But if you use a linear model, this may not be hold. You may go beyond this limit, like less than 0 or greater than 1 also is possible, right? So if you see, yeah, so quantities beyond this range, it is very hard to interpret them as probabilities towards any classes. But nevertheless, they will do the job. Why? Because more value means, towards class 1, less value means towards class 0. Although they cannot be quantified, they cannot be qualified as probabilities, right? By definition, it has to be between 0 and 1. That is the only problem. But if you want to avoid that, obviously logistic regression, what we are going to use, what we are going to discuss, can be used. But so what I want you to notify is basically whatever we have learned can also be used in classification in specific scenarios where there are multiple labels case. If the ordering is natural and the differences between them is also more or less same, then you can use the regression model to classify. Or you have two labels only, then you can model the probability towards one of the class as linear model and then go on training. But one problem in this case is the probabilities may go beyond 0 and 1 because line can take any values, right? Where is that? Yeah, here. If you see, the line can take any value. It need not be only 0, right? So this particular value is less than 0, right? If you just extend, go on extending, somewhere here it will cross y. Sorry, y is equal to 1, right? That also is not a probability, right? That is the problem. When you use linear models in binary case, that is the problem, right? So yeah. The case of logistic regression, that is why we need a logistic regression, because some of the existing regressors fail, and a lot of cases will have, a lot of practical scenarios will have more than two labels. That is why we need it. But anyway, we'll try to understand in a simplistic case, so that you can extend to more classes and more parameters also, right? What is the fund of logistic regression? So it doesn't model the response variable. Why? Because response variable can take only one of the specific values, right? Label values only it can take. So we cannot model it. But instead, what we do is we model the probability that y belongs to a particular category. Let us say there are 3 different classes. I can model the probability for y or input to belong to class 0. or class 1 or class 2. So if you want for all the three, you need three different logistic modelings, right? For each category, right? That is the fundamental, right? For example, I take the credit card balance as the input. How much the customer has to pay at the end of the month. That is my input X. And my output Y is whether the candidate will default or not default, right? So this is what I model, probability for default to be true. It can only take two values, whether default is yes or default is no, right? So default is yes case is represented as probability of balance, right? The default is equal to no will be 1 minus probability of balance, right? So because there are only two categories, it is possible. Otherwise, you have to have another variable. Probability of default is equal to another value given balance. This will become probability of another value, right? So I want you to understand the difference. Because it is only taking two values, I can model it only with one variable. Because for other variable, I can just do 1 minus of this probability, you will get that probability, right? So this is what logistic regression does. It models the probability that Y belongs to a particular category, right? All right, let's see more in more detail. So I just want to recollect what we have done in linear regression case. So this quantity, which is a quantitative response, we model it as beta 0 plus beta 1 x, right? Now in logistic regression, what we are doing is we are modeling the probability for one class, probability that Y belongs to particular class, that is being modeled as a linear form. So P of x, which is probability of Y is equal to 1 given x. You can think of this as probability for default is equal to yes given the balance. So that is the difference. So this is linear regression. If you make P of x as probability of Y is equal to 1 given x, this will become a logistic regression, right? This slide, you need to pay a little more attention. So earlier it was Y in linear regression because our Y itself was a quantitative response. But here in logistic regression, Y is a qualitative where you take labels. So because of that, we model the probability for Y to belong to one class. Here, probability to Y belonging to class 1. I am modeling this quantity as the linear response over X. Right. This is the funda and the difference between the logistic and linear regression also. All right, let us go ahead. So yeah, this is what happens in case of the true probabilities will go out of 0 to 1 range, because line will go on predicting at all the inputs, right? Because of that, the values may go below 0 and above 1, which is not a meaningful probability. So what do we do? So the problem itself gives us the solution. Because the line which can extend from minus infinity to plus infinity will have values beyond 1 and below 0, that is not suitable for us. So how to avoid that? We need a suitable function which gives us responses within 0 and 1 for minus infinity to infinity, right? If you see, I model the probability as a line, right? The probability for Y is equal to 1 for a given input, I model it as beta 0 plus beta 1 x. As I go on changing x, at some point in time, this will go beyond 1 or below 0. So that has to be avoided because I'm modeling the probability, right? So obviously, this cannot be a suitable function. So what I do, I model P of x using a function that gives outputs within 0 and 1. Because this is a probability, this has to be within this range. I'll choose a suitable function which makes my range between 0 and 1. So logistic function is one such function. There are many such functions, but this particular technique uses logistic function. So what is logistic function? E raised to x by 1 plus e raised to x, right? So as you go on from minus infinity to plus infinity, the value of this function will be within 0 to 1. So maximum value itself is 1, close to 1. Yeah, right. So this function, now there is no problem. I can model the probability as the output of this function. That way, it will respect the 0 to 1, right? The probability range, which should be within 0 to 1. Right, let's see. So this is how, after modeling the data of default, credit default, it looks like. So towards, lower balance, it is giving a probability of default to be 0, and towards higher balance, the probability towards default is close to 1. Right? But it is not going beyond 1 and below 0, if you see. So that is what we wanted. So that is the power of this logistic function. So let us see how it will be. Yeah. Right. So what we are doing is basically, instead of probability, yeah. So let me just recap that line. Yeah. Right. Yeah. So the probability of x, instead of just beta 0 plus beta 1 x, which was a line which can go beyond 0 and 1. Instead of that, now you have e power this quantity divided by 1 plus e power this quantity. So that way, this quantity is between 0 and 1. This is logistic function, right? So we moved from line to logistic function. This was simple line, but now we changed it to logistic function. Right? So now if you analyze that function, so what I'm doing is p of x was e raised to this quantity divided by 1 plus e raised to this. I'm just rearranging the formula. If I do p of x by 1 minus p of x, it looks like e raised to beta 0 plus beta 1x. So this particular quantity, so why I am doing this, it will be very clear. So I just did some simple math. Basically, I did e of x by 1 minus p of x. It will look like this. So this quantity, probability divided by 1 minus probability, is called odds in statistics. So odds for x, odds for y is equal to 1 in this case. So this is very famous. Actually, if you remember or if you relate this particular quantity, we do this in real world. People understand this better. What are the odds for India winning against Pakistan, or what are the odds for particularly in horse racing? Actually, what are the odds for that horse number 10? So all that. So it basically tells you probability of that winning or probability of that event to occur divided by probability that other event other than this to occur. There may be multiple events, an event other than this to occur. For example, every 1% in 5 customers will default, right? Every 1 in 5 will default. That means what is the probability? 1 by 5. So if 1 by 5 is put into here, 0.2 divided by 0.8, that means 2 by 8, 1 by 4. So that is the odds for default. You can clearly see every 1 in 5 means it's not much. 1 in 5 means odds are 1 by 4. Let us say every 1 in 2 will default. That means half, probability is half, 1 by 2, right? So if you substitute 0.5 here, odds is 1. Odds is increasing, right? If every 1 in 2 will default, the odds is 1. Let us say every 9 in 10 will default. Such a poor community where 9 out of 10 people are defaulting. They are not paying their credit card bills. What is the probability in that case? It will be 0.9, right? 0.9 divided by 0.1. So odds is 9. That means it's very high that the customer will, generally a customer will default, right? So this is more understandable in day-to-day life, not in the statistical experts. Experts will understand anyway, but in real world, people understand odds. That what they mean by odds is p given p by 1 minus p. It ranges from 0 to infinity because it is very clear, right? So as you increase the probability, the odds will be closer to infinity. I mean, towards infinity, not closer, towards infinity. That way, the strength is understood easily by the common man. So this is called odds. It is required in logistic regression. That is why I'm spending some time on this. All right. So now take logarithm on this quantity. Logarithm on this quantity will be basically log of e will be cancelled and beta 0 plus beta 1x. So now you can see the logarithm of odds is a linear function in X, not the probability itself, right? The probability itself being a linear has a problem of going beyond 0 and 1, right? Now in the modified problem, you see logarithm of odds. It is also called logits. Logits are log odds because we are applying logarithm on the odds. So you may see in CNNs, in neural networks, deep learning, and other related classifiers, the term logits is used more often. So it is related, not exactly the same, but it is related. So what logit means is basically logarithm applied on the odds in here. There, logarithm applied on the probability. Yeah, probability. But anyway, it is very quite related. So you often see the term logits. What it means is it is not the probability directly, it is logarithm applied on that. Or in this case, logarithm applied on the odds. So this is what we need to understand. The linear function is not the probability, but the log of odds, log of odds. All right. So this I want you to relate with the linear regression. All right. So in other words, what it tells is basically, if you recollect, there were some questions in yesterday's last session's example. How much a company who is spending in advertising will come to a statistician or a machine learning engineer, like one of us, will come and ask, how much I have to spend in advertising in TV in order to increase my sales by $1,000 or $10,000. You remember that was also one of the questions we need to answer as a developer. Excuse me. So now what sort of questions are possible here? Now, if I increase X by, let's say, 1 unit, how much my probability is going to increase? Is it linear? Is it exponential? All these things will be answered from this equation itself. Now you can see, if I increase X by 1 unit, right, it is going to multiply my odds by e raised to beta 1, right? So you can also see here, if I add X plus 1 in place of X, that 1 gets multiplied by beta 1, right? My odds get multiplied by e raised to beta 1, not the probability. I can only comment about odds. Or I can comment, if you apply logarithm on both sides, my logits will increase by beta 1. So that much I can tell. If I increase X by 1 unit, my logits will increase by beta 1, right? But I cannot tell directly. I can tell it's a more complicated thing if I want to comment on the probability, right? That is how we have to understand how the input variable is going to affect the probability. So there it was very clear, because every time you increase X by 1, Y was increased by beta 1. If it is positive, or if it is negative, it is going to be decreased. But here, the logits will be increased by beta 1, or the odds will be multiplied by e raised to beta 1. So that is also an important observation we have to make, so that some of the questions will be answered. If I want to increase my odds, or if you want to double my odds, how much the X has to be increased, right? So let us say X plus delta, it will be e raised to beta 1 delta is equal to 2. So delta has to be 1 by delta times log 2. Things like that. You can do all the math. So how much you need to increase the probability by how, and all that. If you understand this relation, you can participate in the game. All right. So this is a logistic regression, and how the probability and the input quantity. For example, in this case, it will be probability for defaulting, and this is the balance. What is the credit card balance towards the end, month end? All right. So interesting property of logistic regression is the function itself. The logistic function itself is very interesting. See, the amount of change in P of X, the amount of change in the probability per unit change in X is not constant everywhere, right? Let us say from 500, so let us take 2 customers. One customer, there is a income of 2,000, not income, sorry, monthly balance towards the end of the month is 2000. Another customer whose balance towards the month end is 2500. You consider these two fellows. So the amount of increase in X here that can cause amount of increase in Y, right? So for example, there is a gap between these two, right? Black lines. So which causes the output to increase by this much gap. So there are two green lines showed, which should tell you the what is the increase in Y for this much increase in X, right? So this need not be the same at all different locations. For example, if you go towards 2500, the same change will be resulting in smaller increase in Y, right? The probability here is not going to increase drastically, but here the probability is going to increase drastically. So this is a function of X. So this increment in Y is not constant everywhere. But if you look at the linear regression where the output response is modeled as a line, it is same. If you take 500 difference here and 500 difference here, the change in Y will be same here and there because the slope is same. So essentially that is the definition of slope, right? Dy by dx, change in Y by change in X. Because the slope of the line is same at every point in X, you need to get the same delta Y for a given delta X at different locations. But here it is different. So that is what theoretically you need to understand. So the change in Y for a particular change in X is not same at every point on the X-axis. It is a function of X. It depends on X. At what X you are considering. For example, if you consider this area, it is almost zero. Whatever you increase within this region, it's not going to change much. The Y, the probability for default is not going to change much. After a while, also it doesn't change much. So this is an interesting property of again the logistic function, which is used in this logistic regression and a lot of other places also, even in deep neural networks and deep learning, people use this logistic function. Yeah, right. So now we understood the properties of the logistic regression, and we understood how the probabilities are modeled, not as a line but as a logistic function, because we need to respect the boundaries of 0 to 1. Right. So now there is another important module in this logistic regression. So once we have this kind of a logistic regression function, so I can model. So let me go back to the equation, which yeah, here. So this is my probability. If I have my beta 0 and beta 1, I can predict the probability for default, how likely this customer is going to default. Default means not pay the bill. If you tell me what is the balance towards the end of the month, I can tell you. That requires obviously beta 0 and beta 1, right? So that is which are unknown at this point in time. They are called the coefficients of logistic regression or parameters of the logistic regression. If you have them, predicting is very easy, substituting the value of X and beta 0 and beta 1 in that formula. So if you just put them, you will find out the probability for default. So similar, this is also very similar to, if you think of, if you recollect concepts from linear regression, there was Y is equal to beta 0 plus beta 1x. Predicting Y is substituting in that, but we need to estimate the coefficients. So how do we do that? We need training data. Similar to any machine learning technique, how the parameters will be estimated, we need data from which we can estimate these parameters beta 0 and beta 1. So this estimation is a little more involved. So without going and without leaving much of the details, I'll discuss in a middle way, so that because that's what I feel. So we get more encouraged if you really understand a little more math behind it. Knowing algorithms intuitively is okay, and another on top of it, we need to be able to use them on data. Practicals is important. The first step is knowing the algorithm intuitively, what is happening, how things work, and what is the important aspects of that algorithm is okay. The very primitive machine learning learners will end up there. but a little more experts, what they do is they know how to implement, how to use the libraries, how to run these algorithms on data. So this is okay. This is definitely okay, because you understood intuitively what the machine learning algorithm is doing, how it is modeling, how it is solving, that you understood, and then you know how to implement and use that also. This is definitely one level of understanding and expertise. But ultimate understanding of the machine learning algorithms will be when you understood them mathematically, when you really know the math behind it. If there is any, some of the algorithms, there is no enough math, although things are understood in different levels. But things like regressions and SVMs and all other machine learning tools, they have good amount of math. This is required to be understood, to complete the understanding of the analysis of this algorithm, right? So that is why I tend to, even in my classes, I tend to introduce this math. Although it is boring, sometimes it may be a little difficult, but I'll try to, feed them in a more palatable way. Okay. So feel free to stop me when you feel it is difficult, or when there is a doubt to understand. I'll try to explain, but we have to do this. Okay. Right. Let's see how we can estimate the coefficients of logistic regression. So if you recollect, how did we do for linear regression? So we tried to estimate the error, which is the difference between the predicted and the estimate. We call this as residual. And then because it can be both negative, or it can be either positive or negative, when you sum over all the training samples, they may cancel out and the error may be reduced. So to avoid that, we squared it so that everything becomes positive, and then we took the sum of those squareds, which is called RSS, residual sum of squared, right? And then we try to minimize it, right? We want such a parameter where we want the sum of these squares to be minimum, right? We just performed a maxima minima. That function, we took partial derivatives with respect to beta naught and equated to 0 and found the value for beta naught. And similarly for beta 1, right? So that is how we did in the logistic regression case. Here, we are going to do something similar, but something different. Let us see. Right. So we generally use maximum likelihood estimation. So maximum likelihood is a very powerful technique in probability theory. It appears in multiple locations, multiple areas where we are doing modeling stuff and try to estimate the parameters, etc., etc. So here in this context, I'll try to explain what maximum likelihood estimation is. All right. So what do we want our parameters to do? It is let us try to understand intuitively. So as a basic understanding, what we want is, we want such betas, we seek estimates of beta 0 and beta 1 such that the predicted probability for every sample corresponds to or becomes closer to its observed ground truth. Is it not? So we want beta 0 and beta 1 to be such that when I apply on any or every xi, the result will be closer to their actual ground truth label, right? Ground truth label means we'll have some training data. We know the balance value and the corresponding label, whether those customers defaulted or not defaulted, whether y is equal to 1 or y is equal to 0, we know. That is called ground truth information, right? So when we substitute x's, so we expect the y's, corresponding y's, y hats, to be closer to y. This is the basic intuition. Every machine learning technique, what we do is we reduce the residual. We try to minimize the gap between the predicted and the true. True is ground truth, right? Observed value or ground truth value, target value. So these are all same. So what we predict should be closer to what we observe. So that is the funda. So you have to keep this in mind. Every machine learning algorithm tries to do the same, particularly classifiers. What is the predicted label? What is the ground truth label? They both are matching or not matching. We want the parameters to make them match, to bring them closer. That is the idea. So as I said, in our example, the label yi is 1 for defaulters, and the label is 0 for non-defaulters, the customers who paid the credit card bill in time. Right. Now, let us try to understand. Consider there are capital N number of samples with labels 0 and 1. Right? 0 means non-defaulters, 1 means defaulters. For samples labeled 1, the estimate of beta. So let us say we will drop beta 0 for some time now. We'll simply say beta x. Beta 1 x plus beta naught is ideal, but we can do that. For simplicity of the analysis, I'm just making it as beta x. We can do the same thing and obtain beta 1 and beta 0. But let's minimize the mathematical equations, the complexity of it. But the funda is same. All right. So we want such a beta which predicts p hat for classes, for the labels that belong, for the samples that belong to class 1. I want all these p hats close to be 1, right? There may be multiple samples. Obviously, if my training data is more, I'll have several samples that belong to default, right? So what I do is, this is the term, basically in the training data, yes, all those samples for which the yi is equal to 1. These are data of defaulters. I want them close to be 1, the p of xi to be 1. So I'm just taking the multiplication. So similarly, for samples labeled as 0, I want p hat to be close to 0. That means 1 minus p hat to be close to 1, right? So this is, a simple mathematical arrangement, because this is also very important. So when you model complex problems in machine learning, what you should do is, we should convert the specifications. My specification is, in case of labeled 1 samples, p hat has to be 1. In case of labeled 0 samples, p hat has to be 0. So I can try some equation with p hat directly, but making it 1 minus p hat will bring me, to an existing framework where I'm already trying to use the product of all close to 1s. So 1 minus px becomes close to 1, and I can use the same thing, right? So this kind of creativity, or some sort of experience is required when you come up with objective functions, particularly in applications like CV, NLP, and text speech processing. There will be different tasks. Based on the task, we should be able to come up with an objective function. Objective is basically which converts the specifications into a mathematical equation. So our specification is like this. As a developer or as a customer, the specifications are like this. In case of sample belonging to defaulter, in case of the data belonging to non-defaulters, p hat has to be 0. So that is where we need our intelligence in converting these into mathematical equations. So this is how here we are converting all the samples that are belonging to default class. I'm taking the probabilities, the product of them, and here all the samples that belonging to class 0, non-defaulters, I want the p of x to be close to 0. So 1 minus p of x will be close to 1. So this I want to maximize, right? In ideal case, this should be 1. This probability to be 1 and this probability to be 0. But sometimes it may not be. But what we want is as maximum as possible. We want to maximize this quantity, right? So consider this as a step towards building up objectives, writing objectives, and solving the machine learning problems. All right, it is a function of beta. Obviously, we need to choose such a beta which maximizes this quantity. But generally, in machine learning, minimization is more, in optimization also, minimization is more studied, and it makes more sense also, as if this is a cost and we are minimizing the cost to increase the performance of the model, etc., etc. So minimization is more favorable. So you can add a minus sign. In that case, you can minimize the formula with a minus sign. Otherwise, maximizing this itself is also same. All right. So this can be rewritten like this. So because we know yi is equal to 1, raising this quantity to power 1 is also same. Here also, yi is equal to 0. I'm raising it to 1 minus yi, which is the same. 1 minus 0 is power 1, and some quantity to power 1 is that quantity itself. Instead of two products, we can have one product. Product of products is same, right? So it's just a simple math. Again, from here where I'm going, I'm applying a log on both of these terms, because if you look at these terms, these are closer to zero probabilities, right? If you have many of them based on your sample training data samples, let us say you have 500 or 1000 data, you are multiplying closer to zero quantities 500 times. Obviously, this is going to be a numerical problem, very close to zero, right? 10 raised to minus 50, minus 500, 600. We're talking about those quantities. So in order to save our sanity, what we'll do is you apply log on both sides. So exponentials become summations in log, right? If you apply log, log of a raised to b will become b log a, right? That is what is happening here. Pi becomes summation. And then this becomes yi logarithm of pi. Similarly, this also, product becomes sum, and exponential becomes multiplication, 1 minus yi times logarithm of 1 minus p of xi, right? So this becomes log likelihood. So this was likelihood. Likelihood, yeah, the other term is likelihood. Why are we calling this likelihood? So what so let me put it this way. Likelihood, you need to understand the term because it appears more often in probability and machine learning. What it means is, what is the likelihood? How likely for this data to appear, right? So you have data. We have data collected from a bank. So they know, they have tracked the credit behavior of some customers over some time. They formed the data set. So it occurred. So it is not something a made up thing. It is real data. So it occurred with a probability, right? So this term is called likelihood because it's a probability to be for the data to be real, right? If it is more, that means this data is more meaningful, right? It's like, imagine a cat with three dogs, 3 legs only. So it is not likely. The likelihood for that photograph or that object is little less, right? So probability with 4 legs is definitely more than probability of a cat with 3 legs. So that is what likelihood means. Because we observed, we expect the predicted probabilities also to be closer. That way it makes sense. Otherwise, it is far from the real data. Likelihood is less for any deviation. If it doesn't deviate, the likelihood is more. So that is the probabilistic interpretation. Basically, you need to understand likelihood means the probability for all of them to be true or for that to occur, right? So this is called likelihood, and because we are applying logarithm on both sides, it is called log likelihood, so that things are numerically stable. We are not going too high or too low, right? All right. So if you just do substitution, you remember P of xi is e raised to b beta x divided by 1 plus e raised to beta x, or 1 by 1 plus e raised to minus beta x. So this is what we modeled, right? Instead of line, we modeled it as a logistic function. I'm just putting the formula. So if you want, you can just, recollect. So this is what I'm doing. So this is 1 by 1 plus e raised to minus of this whole thing. So that is what I'm doing here. Yeah, so P of x means 1 by 1 plus e raised to minus beta x. Here also, P of x means 1 by 1 plus e raised to minus beta x. 1 minus is there, so I'm doing that simplification. So now I can go one more step, doing 1 times this, and then combining these two and separating minus yi times this one. Or yeah, so yi is there, right? I made it common and brought this term here and this term here. So yeah, this is what happens if I just do this summation, because minus in log becomes division, right? I just divide m by n, and this quantity will be just like that. I'm just adjusting this by multiplying. So if you see this, logarithm of e raised to beta x will just become y times beta xi. And here also, just both of them get cancelled, and 1 by 1 plus e power beta x, right? So because 1 by x minus of log x, right? Logarithm of 1 by x is minus of log x. You can just make it as the denominator times power to minus 1. So you can bring that. So the log likelihood looks like this in the end. For all the training data, if you have 10,000 training data, you have to make this summation over all the 10,000, which gives you logarithm of likelihood. So we need to maximize this, right? That is the objective. We need such a beta which maximizes this whole quantity, right? Argument that maximizes this. It is represented as argmax. So if it is minimization, you will have argument, the argument that minimizes this quantity, the whole right-hand side quantity. So this is typically what you see in optimization in machine learning, where you will have an objective function and you seek for parameters that will either maximize the objective or minimize the loss. So this is the fundamental. This is not fundamental, very important step. As a designer, you need to map the specifications into the objective. So how I can realize this function, how I can find parameters of this model which will perform according to the required specifications. So this is how one does it. So it's not solved. We only found out the problem. Now we need to find the solution. So how do we go about it? So this is what I just copied the same equation there. So if you look at this equation, this is not a simple equation. So this is not a simple y is equal to mx plus c, or simply ax squared plus bx plus c. No, it is not a polynomial. It is very complex equation, so which is sometimes referred to as, because it has exponentials and logarithms and all, it is known as transcendental equation. And it cannot be computed exactly, because what cannot be computed, the beta which maximizes this, right? So what you do is, we cannot solve easily. This is where we need to understand optimization sometimes need to be iterative. So just try to recollect what we did in the linear regression case. We get very simple equations, neat equations. You will have beta 0 is equal to something, beta 1 is equal to something. You just put values in those equations, you will get beta 0, and you will get beta 1. That is called closed form solution, right? Where you don't need to anything, only you don't do anything except substituting values in the formula. Those are called closed form solutions. But here, this kind of a problem will not have a closed form solution, right? So what do we do? Recollect again from your +2 and maybe the engineering mathematics. We have to use numerical methods, right? Where we can get only approximate solution, right? So we don't have an exact solution. Maybe it is difficult to find exact solution. So that is when we resort to approximate solutions. Remember, we haven't even gone to, basically we are doing a maximization problem or minimization problem, right? Where you have to find the first derivative and make it equal to 0, right? When we say make it equal to 0, we are finding the roots of the gradient, right? Dou L by dou beta is equal to 0, right? We are finding the roots of that quantity, which is gradient. So that is where we can use the numerical methods, because the complexity of the function, the look of that itself is frightening, right? That's why. So a very quick one-slide revision of Newton-Raphson. So what Newton-Raphson method does is, let us say you have a continuous function f of x, and you need to find the roots of the function. Roots of the function means x at which the f of x becomes 0, right? Where the function crosses the x-axis. That is what is called root. So in other words, we are solving f of x is equal to 0, that equation. So sometimes you will have only approximate solution. You have to go towards the to the actual solution, as much closer as possible. So for that problem, what you do is, from x0, you can make small progress towards the actual root by this equation: x0 minus f of x0 by f dash of x0. This is the first derivative of x. And this is only one step. This process may be iterative, which requires to repeat multiple such steps to get to the desired accurate solution. So in that case, iteratively you move by this equation itself. X of n plus 1 is equal to x of n minus function value at that x divided by derivative of x at that value, derivative of f at that point. So the same, you just do it iteratively. You move from x0 to x1 and x1 to x0 and so on to closer to the actual solution. So this is one method. There may be multiple such methods, Newton-Raphson method. You remember Rangakuta methods, and a lot of things were there. So you can pick one of these methods to estimate the beta, right? So again, so recollect, we are trying to find a beta which will maximize this equation. So what do? We make the first derivative of that equation and equals to 0. That is when we have to apply the Newton-Raphson method, right? So let us see how it will happen. So this is the equation, and this is how the derivative looks like. So once you, so I'll go through these steps, but ultimately it looks like this. Beta t plus 1 is equal to beta t minus the value of the derivative divided by derivative of the derivative, because we're finding the roots of the derivative of this function, right? Dou L is equal to 0. That is what we are finding. So if you do the derivative over the dou L, it will be double derivative, right? So these are computationally little more expensive, not very expensive. Today's libraries are really, really powerful, fast algorithms, and some of them use GPUs where things happen in parallel, and we should not be really worried about the computational complexity or the data size also, right? So that way, this is only for mathematical understanding, but implementation, if you just go find some libraries, they'll do iterative solutions and give the results to us ready-made. So implementation wise, this is not harder. I just want you to understand how we go right from the specifications. As a machine learning practitioner, we should understand from specifications, we need to go to objective and try to find the solutions for that objective. Solutions for that objective is basically the model parameters, right? Which allow us to understand come up with a model, right? So this is what we do. After getting the maximum likelihood, you try to find the derivative and make it equal to 0. Because it is very complex function, you have to apply a numerical method. So there are steps I do have. For example, this is the derivative of the likelihood function. So it's also very simple. Derivative can be taken inside the summation. So you can take it inside, and it applies on the individual terms. And from the equations of yi, you will be able to see how the beta operates and all. So simple +1 derivatives only. So if you just go on doing this, you will end up with solutions like this. So derivative of L is like this, and double derivative of L, which is called Hessian matrix. So there are terms for such matrices. So this is gradient, this is Hessian. So once you have those two formula, X means the training data arranged row wise, Y means the ground truth labels, and Y hat means the predicted P of it. It is also known as P. The matrix Y hat is also known as P. So you can have that also. Yeah. So this ultimately it boiled down to arranging the training data as rows in X and labels in Y and predictions in Y prime. So right. So if you have these two matrices and you just plug in into beta t plus 1 iteratively, you will be able to solve, right? To a required accuracy, you can run, let's say 100 steps or 50 steps, 60 steps, like that. You will be able to find the solution to the parameters beta. So once you have the parameters, all that we can do is basically go here. Yeah. So now you can give the probability for any X. Now the bank, if we're talking about this particular example, so after estimating, the bank will put in X. Tomorrow some new application will come, so he will see he or she will see the X corresponding to that new application, and plugs in this equation and find out what is the probability. So it gives the probability for that customer to default, means not pay. So if it is very high, obviously the bank will reject. And if it is small, because the customer is well behaving and he's a potential customer to earn money, so what they will do is they may give him or sanction him the credit card, right? So this is like that. Once you have the beta 0, beta 1 parameters, you can answer a lot of questions, right? They can understand if there is a change in his annual. Obviously, as employees, we get increments and our salary increases, right? So next year, if his salary is going to increase by this much, how likely is his credit behavior is going to improve by how much, and all that you can plug in and understand. And because of that, things are very much clear, right? So what is happening? It's not like a black box where you can think of a deep neural network with a lot of layers and the filters like that. So we understand and we get a good prediction. Most likely, you will get state-of-the-art results also. But at the same time, it will not be interpretable. We will not have much access inside and much explanation also. But here, simple models will give you clear explanations, and a lot of questions can be easily answered, as I said. And those questions will not be answered in the sophisticated classifiers case. So that is one reason why a lot of industry people are still preferring, in at least some applications, they prefer interpretable models. Because, tomorrow policymakers, these MLAs, MPs, or parliament members, all these guys will be able to understand, what is happening when they want to, accept this algorithm to release the prisoners or give them parole. They need to understand whether this is more meaningful, interpretable, can it answer questions, will it explain its predictions, all those things. That is where, interpretable models like logistic regression and linear regression are very much required. And they are being used also extensively in a lot of such applications. All right, so I hope you guys really understood logistic regression and how we modeled and how derived all these parameters and what makes it explainable. And that way it is better in some sense to all these modern deep learning or any other classifiers also. All right, that is what I have. So now I can discuss if you have any questions about this or the previous module. Okay, I'll also share these slides with you so that yeah, you can also go through just to familiarize these concepts. And once you know these things, and later machine learning techniques are more and more generalizations. They'll find out what is not possible and how to make these models more sophisticated, and the result is other better machine learning techniques. So these are that way fundamental but very important, because everything later, not everything, most of the later developments are generalizations to these techniques. So that is why most of the emphasis is given, even in academia, to discuss these models in detail, particularly in machine learning courses and in research also. Yes.
Excuse me, sir. Good afternoon,
Yes,
sir.
Ravi Kumar Singh, sir. Please go ahead.
Yeah. Sir, my doubt is what exactly regression model is. Because, sir, I have asked in the last session also about some regression model which I see in some literature, and they have used a regression model with different machine learning algorithms.
I remember you, but no, I haven't received any information. Have you sent any? No, right?
No, sir, I didn't send you. Sir,
Right. So regression, let me tell you, the general understanding of regression is basically predicting predicting some quantity based on some independent quantities, right? That is what regression means. Classification means, classifying the quantity into one of these labels. So that is what the fundamental meaning and difference between regression and classification, right? So that way you're saying, I forgot exactly the terms you said, some kernels and something was there.
Multi-kernel regression model, sir. Multi-kernel regression model.
Right. So basically from the words, individual words, so what they're trying to do is regression. They are trying to predict a quantity, a continuous value, right? And multi-kernel means, so imagine, so linear regression, what we did is we modeled the relation to be approximately linear, and then the form taken by y is linear, right? Beta 0 plus beta 1 x, that is linear regression. Now, multi-kernel regression means there are multiple sophisticated functions. Kernel means basically the easy way to understand kernel is an embedding function with a sophisticated embedding function. Let us say line is also embedding, but it's a simple embedding. So let us think of a transformation, right? Wx. It is transforming x into a different space via wx. So that is one kernel. That is transforming x from this space into, let us say wx is going to be a more dimensions. In that case, you are just projecting. That can be a kernel. Basically, applying a transformation or a function on top of an input is called a kernel, right? Now, multi-kernel regression means you are projecting and then performing regression in that space. And you are using more functions. I don't know why. It has to be a specific requirement, the domain knowledge and the problem specifications that are required to understand why they are doing it. They might be, there may be some motivation. They might have explained in that work, but that is what it is. Regression problem, doing it in high dimensions mostly, and multiple kernels are also being used. That means the same X is going through 2-3 functions where the modeling is sophisticated. So may I know more details? What is the application and what is the data there?
Sir, can you please allow me to then I'll show the exact paper
Sure.
where it is mentioned.
Sure. In case, if you want, I can also do search actually, because I am sharing my screen. I can do that also. Multi-kernel regression. Yeah, so we do have some. Okay, I'm getting a warning that.
So the exact paper name is the deterministic and probabilistic wind power forecasting using variational Bayesian based adaptive robust multi-kernel regression model.
There are a lot of adjectives, as many as in the dictionary. Can you please repeat?
Deterministic and probabilistic wind power.
Wind power.
Wind power forecasting.
Forecasting.
Using a variational
Multi-kernel.
Using a variational 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 Bayesian based.
Yeah, there is Bayesian also. Okay.
Bayesian based adaptive robust
Adaptive.
robust
Again, robust.
multi-kernel regression model.
Multi-kernel regression. Because this may be this may allow only to read the abstract, because I'm not with the institute VPN.
If the
Multi-resolution
technical,
data.
yes, yes, it is exactly paper, sir.
Okay. So what happened?
If the technical team allow me for the 2 minutes, can I share my screen?
So, deterministic and probabilistic. So let me see quickly what this is. The original high resolution data is to produce the low resolution time series using Newton-Raphson. Therefore, solution assumption for the user.
Sir, my the main doubt is in which category it belongs. Obviously it is not in a linear regression. It is in multiple regression or a logistic regression. If I want to categorize it,
So, robust multi-kernel regression model, in-power forecasting. So it looks like they're doing regression. Regression means they are not classifying; they are predicting the wind power. In some sophisticated regression model they are using, right? So why I believe that is basically you look at the title, wind power forecasting, right? So they are forecasting the wind power. I don't know how it is measured or what are the units or how it will be, but it looks like it's not classified. Using a variational, and all these are basically whatever augmentations they are using on the basic regression models. But in the end, it is multi-kernel regression model. So there will be, for example, beta 0 plus beta 1 x, right? You can think of more extensions. Because beta 2 times beta 3, beta 4, all these can be different kernels. As I said, right, applying a matrix or applying a transformation is basically one kernel. So if you have multiple such things, based on the requirement, based on the domain knowledge, it becomes a multi-kernel regression, right? You can think of it as extending linear regression with more and more betas, specific betas.
okay.
So that is what it is. So are you working in this area? I just am curious.
Sir, actually, I'm looking for a research title for my project.
Okay. Yeah, definitely. There are still these models being used. I mean, of course, advanced models will be used, but most of them will share the same spirit. Basically, logistic regression and linear regression. What we discussed is the simplest ones, basically to understand the model. But you can do a lot of other stuff. As you see, more independent variables or more transformations on them can be used and all. Yeah. So let me do one thing. I'll try to augment the previous resources with more references so that you can check what variations or what augmentations are possible on top of what we discussed. Okay.
Okay.
Yeah. Thanks. Thank you.
Thank you, sir.
Welcome.
Sir, I have one question.
Sir, just a minute, sir. Ramesh, sir, just a minute, sir.
Okay.
Dear participants, please be informed that we are breaking now. You have 15 minutes of break and come back at 3:30. We will be sharing you a link of assessment examination. For now, you can break for the session. Come back soon. Thank you, everyone. Ramesh, sir, you can continue, sir.
Thank you, sir. Sir, here we are applying a derivative for achieving the desired accuracy, right? In case of logistic regression.
This conference